Hello everybody and welcome to this third video dealing with LPIC 101 exam objectives. In this video we're going to be dealing with objective 101.2, boot the system. We covered 101.1 in the previous two videos and that was determine and configure hardware settings. So let's go ahead and have a look at the information with the details that want us to know about objective 101.2. So if we have a look at the objectives here, we'll see that 101.2 boot the system has a weight of 3. Its description, which is the summary of what you kind of really need to know about this section, is candidates should be able to guide the system through the booting process. So this is basically how the system gets from being powered on to the login prompt. Key knowledge areas: provide common commands to the bootloader and options to the kernel at boot time. Demonstrate knowledge of the boot sequence from BIOS or UEFI to the boot completion. Understanding of sys5 init and systemd. Awareness of upstart. Now, sys5 init and systemd and upstart are what are known as init systems. So we'll talk generically about init systems, what their purpose is in Linux, and then we'll talk about the 3 different types that are available. Also, it's key to know when they say things like awareness, that means just you must be familiar with it or know what that term means. You don't have to know too much about how the actual init system works. Check boot events in the log files. Then the following is a partial list of used files, terms, utilities: dmessage, journalctl, BIOS, UEFI, bootloader, kernel, init ramfs, init, sys5 init, and systemd. So let's go ahead and start unpacking this section. So I'm going to use the following diagram just to give you an overview of how we get from power on the computer to the login prompt. One thing that is happening is a lot of architectural changes that have happened over the last few years at the hardware level for how PC boots up, and the firmware and the various components that are used to get the system into a state where you can log in. So a lot of the PC architecture was defined earlier, had a lot of artificial constraints placed in it because of assumptions that were made about resource usage and resource limits that when the PC architecture was first invented by IBM. And this has been relaxed over the years, but this has led to fundamental changes in the implementation details of how these steps that are involved in booting the system work. In this particular diagram, we're going to see that it's talking about the BIOS as the first stage of the boot process. Now, in your mind, you can replace BIOS with UEFI at this level of explanation. We'll go into more detail later what the difference is between the BIOS and UEFI. Typically, this firmware, I'll use it as a generic term to refer to UEFI and BIOS, can perform a post-test, power on self-test, just to check that everything's okay, there's no memory faults, etc. Then the purpose of the firmware is to load what's called the bootloader. Right? In this particular diagram, we see it referring to the MBR, which stands for Master Boot Record. Once again, this is something which has been replaced in UEFI, and you no longer have a Master Boot Record with the UEFI firmware. But the main point of the BIOS and the Master Boot Record would be for the firmware to locate the first piece of software which doesn't come on the motherboard itself. So that would have been installed at some point when you were installing your system. The bootloader would be installed. So whether you're using an operating system like BSD or Linux, the bootloader would be different at this point. But everything else up to that point would be exactly the same because it's burnt into the motherboard. In Linux, the bootloader is normally called grub, and you'll see here grub2. In this further key objective, we'll look at grub legacy and grub2 and the differences between the two. So once the firmware has started up, it will then load grub, and now grub knows where to go to find the Linux kernel. This is important, right? Because grub itself was a piece of software. There is no operating system at the moment. So grub needs to be able to do things like understand file systems, be able to read disks, to be able to actually load the kernel and something called the initial RAM disk. What grub2 has to do is have drivers to be able to read the partition that you and the file system you installed the Linux kernel on. Now this is normally stored in the /boot directory on your file system. The file that actually is the Linux kernel will be called vmlinux, and that's basically from the early days when VM stood for virtual memory, and then the Z at the end instead of Linux is because it was a compressed image. So it's kind of stuck around as vmlinux, even though everybody's using virtual memory these days, and it's not something which is which is different between different operating systems. So that's where the name vmlinux comes from. Now, when the kernel, when the bootloader loads the kernel needs drivers to be able to read disks, initialize hardware, etc. And as we looked at in 101.1, there are lots of different drivers out there, so the kernel doesn't know what drivers it's going to need to boot the system. You could compile all of the drivers into the Linux kernel, so when it boots it up, it'll have everything it needed. But there's far too many drivers for all of the vast array of hardware that's out there. So what happens instead, the drivers that are necessary for the Linux kernel to be able to boot itself up are stored in an image called init RAM-fs, or initial RAM disk. This is essentially a copy of all of the kernel modules that is needed, and this is loaded into memory as a pseudo disk or a RAM disk. And then the Linux kernel is pointed to this RAM disk where it can go to find the modules that it needs. So this will differ from machine to machine depending on what hardware that machine has. So for example, if you have a disk that is an RAID configuration, needs a RAID controller driver, then that will be in the init RAM-fs if it's not compiled directly into the kernel. However, if you're booting off an NVMe drive, you need a different driver, and that will be in the init RAM-fs. So once those two components have been loaded into memory, then grub hands over to the kernel, and the kernel takes over. So just to kind of reiterate, the BIOS gets loaded first. Its job is to initialize some hardware, find the bootloader. Once it loads the bootloader, it disappears. The bootloader takes over. Its job is to find where the kernel is. Once it's loaded the kernel and initial RAM disk, it hands over to the kernel. The kernel then starts to boot, initializing the system, initializing hardware, etc. And then once the kernel has finished loading, it then needs to hand over to what's called the init process. Now the init process is that part of the system which is responsible for starting up things like the mail server, the web server, starting the getty process for the login prompt, or starting X Windows or Wayland, and then presenting you with a GNOME login prompt or KDE login prompt. So the initial process is the init process is the first process that starts up on Linux, and it is the parent process for all other processes that run on your system. So there's a whole lot of concepts that we have kind of mentioned there at a very high level that you're going to keep on coming across again and again in your journey in understanding Linux. So let's start to unpack some of those. So just to give you some practical idea about how this works, let's examine the boot process as it occurs in a virtual machine. So yeah, we have a virtual machine which I've set up. I'm just going to reboot it, and then we can see the process as it is starting up. So it's just shutting down. Now what we're not going to see here is the BIOS, because it's a virtual machine. There's the C BIOS, but it's obviously not a proper BIOS, so I can't go into the BIOS and show you the settings, but I'm sure you're familiar with having gone into the BIOS yourself on your own machines to kind of examine the hardware settings, etc. And this once again is one of the first differences between BIOS and UEFI. Just a quick overview of UEFI and the BIOS, what the differences are. UEFI is far more powerful than the old BIOS, right? The old BIOS was very limited. It didn't load a lot of drivers to handle the mouse, etc. If you boot up into UEFI firmware, you'll find that you almost got a GUI desktop to work with in terms of configuring the hardware. So it's almost like a mini operating system that allows you to configure the hardware. Besides the sort of obvious visual differences between BIOS and UEFI, there's a lot of differences in the way it handles finding the bootloader and then loading the kernels from there for the different operating systems. But we'll discuss that further after we've had a look at this section. So the first thing that we see here that we come across, and I pushed escape quickly to interrupt the process, is to see the grub bootloader menu. And then typically in grub bootloader, you'll see that we can select a different operating system or different versions of the current operating systems to boot. Since it's a virtual machine, I don't have multiple operating systems installed on it. I've only got Ubuntu installed on it. Now, in a further objective, we're going to be looking at the grub bootloader and how you go about configuring the bootloader. Also, one of the objectives I want you to know in this section is how to pass kernel parameters through to the bootloader at boot up time. And this is where, if you're on the grub bootloader, you can push E for edit and go in and change the parameters that get passed through to the kernel. Now, there's a lot of information around grub2 in terms of what it's doing here, record, fail. These are functions that it's defined, like load, video, etc. What's important, at least for LPIC 101, is to sort of see this line here which says Linux and initial RAM disk. So as we can see here, Linux is telling it where to go find the Linux kernel, and it's saying what you're going to find it under the directory boot VM Linux. So we discussed VM Linux already. Then we've got the version of the Linux kernel that's running here. And this is where you go to find the initial RAM disk. Now once I boot the system up, we'll go and have a look at the boot directory, and we'll see that these two files actually exist. One of the key things to note here is that this is a path to a file system. So it's a bit of a chicken egg scenario, because to know how a file system works, you need to have a driver for that file system. So this means that Grub has to have its own set of drivers to be able to read this particular file system. And this is why you might find, especially in Grub Legacy, it can only understand a limited number of file systems. And if you want to use a more esoteric or more exotic or a newer file system, Grub Legacy might not be able to see it, and therefore might not be able to find your kernel and your initial RAM disk, and therefore cannot boot your system. And by the way, this is what they want, why they want you to know this process, is when you're troubleshooting boot issues. Like, at what point is it failing? You know, if, for example, it can't find the BIOS, well, then the motherboard's gone, right? But normally it'll find the BIOS. After that, it might find Grub. If it comes at it, I can't find Grub, then you know, hey, you have to reinstall Grub. If it finds Grub and then Grub says, well, I can't find the kernel, then you know either the disk is missing that the kernel's on, or Grub has some problem reading that particular disk. And then as we look later, once it finds the kernel and the initial RAM disk, and it boots up, and then it fails at that point, saying, listen, I can't find the init system, you then know that the init system has been misconfigured, and you have to fix up and troubleshoot problems with the init system. So, in terms of what are the objectives, and we'll come back and look at this a little bit detail later, we have to pass parameters through to the Linux kernel. This is where we can do it. We can already see how there are several parameters that are being passed through, such as read-only, right, for the boot disk, for the Linux kernel. And we'll come through and pass the extra parameters. In particular, the one that I want you to know about is passing through the parameter single, which will boot the machine into single user mode. This is for cases where you've forgotten things like the root password or need to do system maintenance. Anyway, I'm going to continue with the boot process, and I'm going to tell Grub, yes, Grub, the BIOS has been found, the BIOS found Grub has been configured, and tell it where the different kernels are. So load this kernel. Now it's going to load the kernel, and then we'll see the kernel starting up and a lot of stuff shooting by quite quickly. This first part before you get the green OK is all the kernel. So the kernel, you'll see when we look at dmessage, which stands for diagnostic message, and dmessage gives us information that the kernel, dmessage gives us information that the kernel exports about activities and events that are happening, or the log information from the kernel. Once the kernel has finished initializing hardware, the kernel is configured to go find the init system, and in this case it's using systemd. So it finds systemd, and systemd is configured to start up all the different services, and one of the final services that starts up is the getty process for me to be able to log in to the system. Okay, so let's log in and have a look at dmessage, the log file, so we can see what the kernel did initializing hardware. Okay, so let us log into the system and see what dmessage or diagnostic message does. That's one of the key terms that they want you to know. So the user as demo, let me just log in. If I type dmessage by itself, we are going to see output scroll across the screen. This is the output that we see when the kernel boots up. So the kernel logs messages. Once again, we have this chicken egg scenario because the kernel is logging messages. But where does it log it to? Because it hasn't yet loaded the file system. So I can't write it to disk. It also cannot use the built-in Linux login subsystem or syslog because it hasn't been loaded yet. So the kernel has to have its own logging system. And these will eventually get written to the syslog daemon as well, so that it can be saved to a file and used later. But dmessage is going to query what's called the ring buffer, the kernel ring buffer, which keeps all of these messages. Because the kernel can't write to disk initially when it's booting up, because it doesn't have the drivers, it hasn't even, as part of the init process, it hasn't loaded or mounted the root file system yet, it will write it to memory. It's called a ring buffer because it's a fixed set of size memory that's set aside to actually keep log messages. And once that memory is filled up, then it just simply overwrites the oldest message in the log. But before that happens, of course, the system should have booted up and the file system should be mounted and the log or the kernel buffer can be flushed to disk. Okay, so in this particular output, one thing you might sort of see different from other machines is that systemd is colorizing. It's in actual fact systemd is taken over and colorizing the output for us here, but it's coming from the kernel. Now, what you'll notice is that these are only kernel messages. So if I was to pass this through a command called less, you'll see that it's doing things like initializing, finding the BIOS tables, initializing memory, APCR, etc. Obviously, there's a lot going on here in terms of hardware. You're not expected to know all the different subsystems and how that all works at a kernel level, but it's always interesting to, this is one thing that's nice about Linux, it's always interesting to find out more, read up how these different subsystems work, how the different modules interact with those subsystems work, and what parameters you can pass through to those subsystems and modules to be able to configure the hardware the way you want. Okay, now if I went and I said tail var log syslog, now syslog is the system logging system it's a system logging subsystem in Linux, and this is like the event viewer in Windows, where all of the applications and kernel messages get written to. So far dmessage just showed us kernel messages, but syslog will show us kernel and application messages. So if I less that, we should see the same output written to syslog. And eventually, once we get to the end, after the kernel has initialized everything and booted up and handed over to init, we'll start seeing messages that don't come from the kernel. So let me just get to the bottom. Yeah, we can see started. This is where we can kind of start seeing that the init system has taken over. Because if you look here, we start seeing systemd logging to this syslog. One of the things I would like to show you here is, when we looked at the grub bootloader, we saw it referring to the boot file system, and then to VM Linux, and then to the initial RAM disk. So if we kind of go ls boot, yeah, we're going to see the Linux kernels. So yeah, we have VM Linux -4.4.0.151 generic kernel. We'll see there's a number of kernels here, because as we upgrade the system and do a system update, newer kernels come, the older kernels remain. Why is that? Well, if you update the kernel and there's a problem and you can't boot your system, you need to be able to go and boot an older version of the kernel. So there should always be at least the current kernel and one previous version, so that if there are any issues, you can always boot the older, known, good version of the Linux kernel to be able to get into your system and then recover it. We'll see that for every new kernel that gets installed, a number of files get generated, like ABR, config, and the one that we're really interested in is the initial RAM disk, init.rd. So I said, it's basically a compressed file, a zip file, an archive file, a compressed archive file that contains all of the drivers that are needed by the Linux kernel to be able to boot the system. Now this file gets discarded after the Linux kernel has finished booting, because the Linux kernel can, once it's mounted the root file system, can actually read the modules from the root file system, no longer needs the initial RAM disk, and it gets discarded. So it's only a temporary file that gets loaded into memory, gets unzipped, gets mounted as a file system and provided to the Linux kernel. Because what it's really looking for is all of the drivers that need to be able to mount the disk and actually read the disk with where the modules are stored in Linux. So just to kind of demonstrate that, let's have a look at the Linux modules. So where are these Linux modules stored? When they're on disk, well, if you go to lib modules, you will see there we have a directory for each one of the Linux kernels that we have in the boot folder on our system. Because each Linux kernel has its own version of the Linux drivers or Linux modules. If we then go into one of these directories, we will see that there are a whole bunch of different folders underneath here that contain the drivers that Linux uses to be able to manage hardware. Really what we're interested in is going into the kernel, going into the kernel directory, drivers, and then you're going to see a whole bunch of folders for each of the different hardware subsystems that are in Linux. So for example, if we went into USB, we're going to see this further broken down in there. And if we were to choose, for example, let's take common, we're going to see drivers. Now these drivers end in KO, which stands for kernel object. So you can play around and have a look at these directories. You'll see the different drivers that are there that for the different pieces of hardware that Linux has to configure and use. But that is just an overview of how the Linux kernel finds its modules, what the point of init ramfs is, because let's say this USB common driver that it needed, if it needed that to boot up, how would it be able to use it if it was on the file system but it couldn't yet mount the file system because it doesn't have the driver for the file system? So it's a chicken egg scenario. That is why initial RAM disk exists. So let's just have a quick discussion about the difference between BIOS and UEFI. And this information we built upon later as we look at things like installing grub. So if we have a look at this diagram, at a high level it explains some of the differences between the BIOS and UEFI. So when the BIOS starts up, it's going to look for something called the master boot record, MBR. The master boot record is normally the first sector of the first or the bootable disk, and which is a bootable disk. While you go into the BIOS and say boot this hard disk. So it's the first sector of the disk that contains essentially the bootloader, which will be grub in our case. And as we can see from the diagram, the bootloader is going to find the kernel, and the kernel is responsible for booting the operating system. In UEFI, Unified Extensible Firmware Interface, the firmware is much more comprehensive. It's not as limited in size as is the BIOS. So it can do a lot more. And it looks inside what's called the ESP partition to find bootloaders. Now don't get confused, because this is bootloaders are different to the grub bootloader. It's a little bit circular how Linux handles EFI boot partition. Because in EFI, you would actually load the bootloader for the kernel, for the operating system in the ESP partition, and then that should boot the kernel directly and then boot the operating system. In Linux, if you've got grub installed, EFI will load grub, which is also a bootloader, which then goes ahead and loads the Linux kernel. So a little bit of a redundancy there in terms of how grub 2 operates. Because the UEFI can also present you with a menu of what operating system you want to log or you want to boot, just like grub can do. However, it can't do things like allow you to change the parameters to the Linux kernel. And another problem with the UEFI bootloader menu is that it differs from system to system. So some manufacturers will have push a key and it pops up. Others you might have to go into the firmware by pushing escape or delete, etc., and then change what operating system you want to boot from within the UEFI firmware, rather than doing it from a menu that gets presented to you at boot time. So this is why in Linux we still tend to use grub 2. We still tend to have our own boot menu presented to us via grub and managed by grub, rather than having it completely managed by UEFI, although you can configure it in both places. So let's talk about init systems. I'm going to switch back to my virtual machine. Now the purpose of the init system is to start up all of the applications that you have configured to start at boot time. So the kernel initializes the hardware. Once the hardware is initialized, it has to mount what's called the root file system, and obviously needs drivers for that. And the root file system is basically the disk on which your operating system is installed. So once again, just to kind of repeat myself, you've got a chicken egg scenario because the kernel is on the disk already. So how does the kernel get rid of the disk? Well, as I said, grub has drivers that can understand the file system. It finds the kernel, loads it. But now the kernel doesn't have all its modules, so it has the initial RAM disk. It can then understand and mount the file system, and then it can access all of the files that it needs on that disk. But once it's finished its job, it needs to say, well, what else needs to be done? It then hands over to the init system. Now in Linux, there are 3 init systems currently. Well, there's a lot more, but there's 3 main ones. The one that's dominant at the moment is called Systemctl, and it has replaced the older init system called System5. Now Sys5 or System5 is many years old, and for many years it served the Linux community, the Unix community in general well. But with the advent of things like smartphones, microwaves and TVs running Linux, etc., we needed a way to be able to boot the system in much more quicker mode and a much performant manner than was done with System5. And this is where a whole bunch of competing systems came about, init systems, to try and speed up the process and modernize it. The 2 main competitors in this space were Upstart and Systemctl. To cut a long story short, Systemctl won what was called the init wars, and it has become the default init system used across most Linux distributions today. It's a bit difficult to demonstrate some of the Sys5 init processes because it's largely been replaced by Systemctl on most modern systems. You might ask, why do you even need to be aware of it then? Well, you might come across a server that's been installed 5 years ago that is still using Sys5 init process. However, this move to a new init process, is a gradual thing. So there's still a lot of vestigial Sys5 processes and init scripts lying around on the system, which you'll come across even if you're on a system that is relatively modern and running Systemctl. So I'll start with Systemctl because it's easier, then I'll show you some of the init or Sys5 init files and configuration files that exist still today. So I'm just going to clear the screen quickly so we have Okay, so what is systemd? Well, systemd is mainly accessed via the systemctl command. So if I type systemctl, I'm going to get a list of all of the processes and configuration files. We'll go into a bit more detail later about the different types of configuration files you have around systemd. That systemd has been set up to initialize this particular system and start processes, do things like mount file systems, etc. So one of the main things you're going to come across with init systems is starting and stopping processes. So in systemd, this is with the systemctl command. And for example, like a systemd status, and I say something like Apache 2, it will come back and tell me that this is the state of Apache 2, it's started up and it's active. I can stop and start processes with this, so I can go and say stop Apache 2, and that will then stop the Apache 2 process. It's prompting me for my password, so I have authenticated and it will stop the process. I can also start a process with start and then the process name, and the process will now have started up. Other things you can do with systemctl is if you want to see, well, what is started up when the machine boots up, you can say list dash units, and then you can say dash type service. There are different types of files in systemd. The ones we're interested in, at least at this level, is the service files. These are the ones that configure, do you want Apache to start at boot up or not? Maybe you want to start Nginx instead of Apache. What we can also do is use systemctl to enable or disable a process to start or not start at boot up. So currently Apache 2 is set to start at boot up. So I can say disable Apache 2. And that will then mean that Apache 2 now won't start up when the system boots up. I can also use, obviously, enable to enable it, to say it must start up when the machine boots up. Now, if you're using a different distribution other than Ubuntu, it might not be called Apache 2, for example, and CentOS is called HTTPD. So you'd have to go systemctl disable HTTPD, depending on what distribution you're using. So that's really what you need to know for systemd. Just to give you an example of some of their configuration files. Let's quickly go and have a look. If we go ls etc systemd system, we're going to see that there are a bunch of files. If we just quickly have a look at the sshd service file here. We're going to see a typical what's called a unit file. It's going to have a description, in the unit heading, which is basically metadata information about the process. Then under the service section, we have things like the environment file that's going to use set environment variables. But just from a simplistic point of view, we're going to actually have the exec start command, which does use user sbin sshd. Well, we want to start the SSH service, so here's a program, please start this program for me. Okay, now the oldest is 5. So the configuration files are under etc systemd. There are several locations for systemd configuration file, but this is the one that you kind of should be aware of for the exam. If we have a look, you will see under etc, if I go ls, we're going to see a whole bunch of these. Unfortunately, I can't highlight it. It's a bit difficult to highlight it in the virtual machine. But if you look on the second to last column from the right, you'll see there's rc0.d, rc1.d, rc2.d, rc3.d, etc. These are called run control directories, and they'll correspond to what are called run levels in the old sys5 init process. So sys5 had these different levels you could boot into, 1 to 6, or 0 to 6. And only 3 and 5 were really used by everyday users. Level 6 would be reboot your system. Level 1 will go into single user mode. Level 3 will go typically into multi-user mode without a GUI, and level 5 will go into multi-user mode with a GUI. And so you'll configure, depending on which run level you were going to boot into, what systems you wanted to start up, when applications and services you wanted to start up when you went into that run level. It does seem a little bit odd why there were these different run levels, but that's the concept that System 5 used to control what booted up where and what different configurations you could have for different run levels. Now, if we have a look inside these files, you'll see, like let's take rc3.d. We're going to see a whole bunch of scripts that got S in the front for start, and then a number, which is the order in which they'll start up in, because there's dependencies, right, when you're starting systems. For example, you first need to start a network before you can start Apache. When you start Apache service, there's no network. Obviously, Apache is not going to load. So there's dependencies between the systems, and the way that was done in the system file was via the naming of these script files. And what's nice, these script files are simple bash scripts. Well, maybe not so simple. That's one of the advantages of systemd. People find it easier to write systemd unit files or service files to be able to create applications to run at startup, whereas in old days it had to be quite a bash guru to be able to set up a robust bash script to start and stop a service with the init system. So let's say O2 Apache 2, right? There's a file there, that's to start Apache 2. And if we have a look at the contents of this file, we're going to see that it's a bash script. And it goes on for several pages. It's what intimidated people about writing robust bash scripts for the System 5 init process. But it was quite loved by administrators, because if you knew bash, you could write a bash script. And bash scripts are ultimately very flexible. One of the main configuration files you might hear people talk about, which was used to configure System 5, was init tab. The init tab file you're not going to find on any systems these days. If you do find it, it'll just be a stub file. So in this particular version, this is Ubuntu 16.04, which is quite old and doesn't even have an init tab file in it. If you do find an init tab file, it might be empty. On older versions, it was a file that controlled what was the default boot level. For example, it's one of the things it could do. What was the default boot level that the system would boot into when System 5 started up? And if you wanted to change it from 5 to 3, you would go into that file and edit it. Also controlled several other things like what Getty processes started up and what virtual terminals, etc. But for the exam, just have to be aware that the file was called init tab. What you can also see here when I went ls etc init, there's a directory called init, and this is leftovers from Upstart. It also had its own way of interacting with the init system. Instead of using Systemctl, you would use things like initctl rather to control and interact with the init system. In terms of the old System 5 commands that we used to configure System 5, we have things like service, and these commands will still work today because they've been retrofitted. But you'll say service like Apache 2 status, okay, or service Apache 2 start, or service Apache 2 stop. And what you can see here is, in fact, it's using the systemd subsystem to start it. So even though Apache has got a init system, a System 5 init file, it is controlled by systemd. Okay, so if I wanted to enable and disable services, that would depend on what distribution I was using. On Ubuntu, I would have to use update rc.d script to say how I want to enable this Apache to run at startup or disable it. In Red Hat based systems, I'd have to use checkconfig, chkconfig to be able to do that. This is one of the things with System 5. There were different tools for different distributions to do things like configuration. With systemd now, it's universal across all distributions, using the same set of commands to enable and disable services. So I've forgotten the username and password for the system, so I'm going to use it to demonstrate resetting the password by going into what's called single user mode. Now, you go into single user mode in Linux by passing a parameter to the kernel via the grub menu, and it's simply single. And this will then boot the system without asking or prompting for a password, and you'll be logged in as the root user. Now, this might be considered a security issue, so you can configure grub and the boot process to ask for a password to go into maintenance mode. Of course, this obviates one of the benefits of having single user mode, which is to reset a forgotten root password. So if you have that set up and you can't log in, then the only way to reset your password would be to take that disk out of the machine, put it in another machine, boot it up, do a root environment, and then change the password that way. And the argument is, well, why not put a password on there? Well, you have to have physical access to the machine to be able to get to the BIOS and to be able to pass single parameter through to the kernel. Of course, there's also debatable these days, because with lots of virtual machines around, where actually is the console. So, as you can see, there's lots of debates and security issues and things to consider in Linux. But for now, we're just going to look at passing the single user parameter through to the kernel at boot time. So what I'm going to do is reboot the system. and then I'm going to push escape to get to the grub prompt. So it's shutting down. Sometimes you have to be quite quick to push escape to get the prompt. If you miss it, you have to boot again. In some systems, you might have to push a different key combination, like tab or shift tab or something like that, to be able to get to the grub prompt. Now, grub can be configured to show a prompt and wait a certain timeout value or not. In most cases, especially on desktop machines, it's hidden because you don't want to kind of show your average user a whole bunch of kernel messages scrolling past the screen and your system messages scrolling past the screen because they find it quite scary. So it's hidden behind some kind of splash screen. But if you look for your particular distribution, you should find information on how to get to the grub boot menu. In most cases, it's a case of pushing escape. Okay, so I'm going to go on E for edit here. And I'm going to scroll down to the line Linux that we mentioned previously. And at the end, all I'm going to do is space and type single. That's all I do, and then you'll see at the bottom there's a number of options for you to what you want to do to get out of this menu. So it says minimum Emacs like screen editing is supported, tab list completions, press Ctrl X or F10 to boot, Ctrl C or F12 for a command line, or escape to discard changes and return to the grub menu. So we want to boot the change that we made, so I'm just going to push Ctrl X and it should boot. Now what we'll see, it'll look pretty similar to what we've seen before, but we're going to see that it will dump me to the command prompt, and if I type who am I should be the root user and then be able to carry out system maintenance and change on the system. So here we can see it says welcome to rescue mode. After logging in, type journal ctl -xp to view system logs, and it says or press Ctrl D to continue. So I'm just going to push enter to get maintenance mode. If I type who am I here, I'm going to see that I'm root. So now I can go ahead and reset the password for the user that I have forgotten. Okay, so let's go and have a look and see what we have still got left to cover in our objectives here. To provide common command to the bootloader and options to the kernel at boot time. So we kind of saw that with the single user command. Demonstrate knowledge of the boot sequence from BIOS UEFI to boot completion. Understand the sys5 and systemd process. Awareness of upstart. And check boot events in the log file. So we've done that with dmessage, etc. The following is a partial list of used file terms and utilities. Dmessage, we had a look at that. Journal CTL, we haven't had a look at that yet. We'll do that now. BIOS UEFI, we've covered. Bootloader, we've covered. Kernel, we've covered. Init ramfs, we've covered. Init, we covered. That's the init system, right? sys5 init and systemd, we covered. So let's quickly have a look at journal CTL. So journal CTL is a way to access the logging system via systemd. So if you type journal CTL, we're going to get the same messages that we get from varlog syslog. We can use journal CTL to do things like list only for a particular unit. If I only wanted to see stuff for Apache 2, I could go journal CTL-u Apache 2. And then I'm only going to see log messages relating to Apache 2. Now there's many things, same with Systemctl and journal CTL. There's also options and parameters that you can pass through to these commands to have to get more information and interrogate your system further. For the exam, all you need to know is the basics. But what I can show you with journal CTL as well, one of the ones I like you to do is to go -B. B says show me just the boot messages that I saw when the system booted up. And if you set Systemctl up properly, or journal CTL up properly, you'll be able to see boot messages from the different times when you rebooted your system. So go back in history to see what changed in terms of booting your system up and down. I don't think from a system administration point of view that's important, but they like you to know about it. Because I think if you're an operating system developer, it's quite useful. You've got a new kernel, what changed? Why didn't it initialize properly? What last time this hardware was working? So you can kind of compare the boot messages between the system when the system booted up. These are just the messages from the kernel itself. You can also do things like go and sort of say, I want to do from 10:30. Oops, I got the command wrong there. I always get confused because we kind of use from until. It's actually since. So we can go --since. Put 1730 there. Let's just say 1700 to 1734. It'll give me the messages that were logged at that particular time. So journal CTL is quite a useful command to be able to interrogate and find information. So the overall objective here is to be able to query your system, find information about where it's gone wrong to be able to troubleshoot and fix any problems that might arise during the boot process. And we're going to see more about the boot process and how particular problems can be fixed in the following objectives. Thank you.